Okay, Assalamualaikum warahmatullahi wabarakatuh. So last time we already finished our class on major losses. So today we are going to continue where we left off with minor losses. So this time we are going to see what is causing minor losses. Okay, minor losses is caused by various fittings, valves, bands, elbows, teeth, inlets, exits, expansions and contractions in addition to the pipes. These components, they will interrupt the smooth flow of the fluid and cause additional losses because of the flow, separation and mixing they induce. In a typical system with long pipes, these losses are minor compared to the head loss in the straight sections, which is the major losses, and we call them minor losses. For example, flow through valves and fittings is very complex and a theoretical analysis is generally not plausible. Therefore, minor losses are determined experimentally, usually by the manufacturers of the components. And basically, minor losses are expressed in terms of the loss coefficient, or we call them KL. Okay, this one. So KL is expressed as HL over V square over 2G. Okay, so if we want to find HL, we can just bring this one to the left side. So we come KL V square over 2G. So this is what we have to find minor loss. Where HL is the additional irreversible head loss in the piping system caused by insertion of the component. And the head loss is defined by KL, which is the loss coefficient, times V square, which is the velocity, over 2G. Yeah. Okay, so from this figure, if we have two pipes over here, one pipe is connected using a valve, while one pipe is connected with a straight constant diameter pipe from location 1 to location 2. So the delta P or pressure drop, delta P loss equals to P1 minus P2 that is caused by the valve. Okay, for this picture, the delta PL or the pressure loss is P1 minus P2 that is caused by the pipe. Okay, so to find the total pressure loss, okay, so the pressure loss is P1 minus P2 valve minus P1 minus P2 pipe. Okay, so next, let's look at some of the loss coefficient KL of various pipe components that is shown here. Okay, so we will have a lot of components that we can use in our system. So one of it is pipe inlet. So we have pipe inlet that is re-entrant because the inlet is inside the tank, maybe. Okay, so this one will have a larger loss coefficient, while the sharp edge will have larger loss coefficient compared to the well-rounded or slightly rounded loss coefficient. While the pipe exit also have re-entrant and sharp edge and rounded edge. Okay, so for pipe exit, we also have re-entrant KL equals alpha, sharp edge KL also equals alpha, and rounded KL equals alpha. Okay, the kinetic energy correction factor is alpha equals 2 for fully developed laminar flow and alpha equals 1.05 for fully developed tubular flow. So basically, this is something that you don't need to worry about because usually the K value will be given in your questions. So if you look at past year examination questions, usually the KL value is given because sometimes even though the typical value is this one, it also changes with the type of pipe and things like that, because we don't know what is the R over D and whatnot. So usually the KL value is given in the question. Okay, we also have, so I just want you to show you the type of the components that we have. Okay, we also have sudden expansion. Okay, based on its name, you also know sudden expansion is the pipe type expand. Okay, from this one, at the entrance is a smaller pipe diameter, while at the outlet is a larger pipe diameter. Okay, so we have this is called the sudden expansion. So from a larger pipe diameter to a smaller pipe diameter is called sudden contraction. Okay, so we also have gradual expansion and contraction based on the velocity in the smaller pipe diameter pipe. So basically all of the KL values is different. Okay, besides that, we also have bands and branches. We have 90 degree smooth band. Okay, this is a 90 degree smooth band. We have meter band without veins. We also have meter band with veins. So meter band with veins have lower coefficient, loss coefficient values compared to meter band without veins. Okay, and then we also have 45 degrees threaded elbow, 180 degrees return band. We have T, branch flow, line flow, and threaded union. Okay, so basically we have learned the equation that we need for major loss. So when we want to find the total loss, we can just add all of the losses. Okay, so if it is a one pipe loss, if it is a one pipe system, you can just add one head loss value. Okay, so if it is a two pipe system, you can just add one head loss 1 major plus head loss 2 major plus head loss minor. Can case like that lah. Yeah. Okay, so if the entire pipe system is of constant diameter, you can just use the total head loss equation to this one. So if this is what you use when it have a constant diameter, but if it is not a constant diameter, you cannot use this. You can you need to calculate one by one. You need to calculate HL major first, and then you calculate the HL minor. Okay,